let's move on to the final topic, which we will study the transient behavior about the Markov chain. What are we going to talk about? So in the previous lecture, what we were doing was that a Markov chain with a single recurrent and aperiodic class, right? And we observed that in a single recurrent and aperiodic class, every state will be visited an infinite number of times. We will run the Markov chain for a long time. So the natural question would be to study the steady state behavior, meaning that since every state is visited infinite number of times, maybe there will exist some relative portion of how frequently we visit each state, right? So the question was that what are the long-term average frequencies of the states? That was a natural question that comes from our observation. So that's why we have defined something called the steady state probabilities. And also we have studied how we compute those steady state probabilities. But in this lecture, we're gonna study a different thing. So in this lecture, we go back to a more general Markov chain. And general Markov chain will consist of the multiple recurrent classes, say like R1 up to the Rk, and also a set of transient state, right? And then let's assume that we start from a state in the transient state, for example. Because the reason why we're looking at this case is that if we start the Markov chain as some recurrent state, then that Markov chain will visit the states only in that island, in that recurrent class. So there's no interesting questions about when we study that thing, okay? So what we are going to do is that let's assume that we start from a state in the transient state, then the interesting questions happens. What is that? So the transient state will be visited finite number of times. That's the definition of the transient state, right? And then the Markov chain will enter a recurrent class, whether it is R1 or R2, maybe Rk, some recurrent class, and then whose states will be visited in number of times. So starting from the transient state, depending on the probabilities at random, then somehow I will enter some recurrent class, and then I will visit the recurrent state at that class infinite number of times. But other states in other recurrent classes will not be visited. That's what will happen if we start a Markov chain from a state in the transient state, okay? We are interested in studying this transient behavior. What is that? So for example, what is the first recurrent state to be entered? It's possible that I can enter this recurrent class or this recurrent class. There will be a different probabilities. So studying these probabilities will be very interesting. And also, what will be the time until this happens? Okay. So we say that this is a transient behavior, right? Why is that? Because when from the time when we start the Markov chain, we just look at until this Markov chain enter the recurrent state. So it's a transient behavior. It's not something that we run the Markov chain for a long time. We just look at the sort of the first a set of a finite number of steps until I'm at some recurrent class or I'm at some recurrent states. So who are the targets? That's the probabilities that I can enter some recurrent class, and also the time until this happens. That's a transient behavior. So, okay. So we're going to talk about this thing. All right. Now we are going to ask a few questions that we are interested in. So first, let us start from a very basic question about this transient behavior, right? So this is our strategy. So rather than dealing with a general Markov chain, so what is a general Markov chain? Multiple recurrent classes and then transient states. A set of the transient states. Okay, that's the general Markov chain. But we're going to restrict our attention to some class of the Markov chain, which is the Markov chain that every recurrent state is so-called observing. What is the definition of observing? So state K is, we say that is observing if it has a self-transition probability that is equal to 1. So that means that what? Whenever I enter that state, I will stay at that state forever. And then the probability that I go out from K to other states, that's 0. When you look at this Markov chain, we have two observing states. That is 6 and that is 1. Because there is a probability of 1 of self-transition. Here's again the self-transition, and it does not go out because there's the probability 1. So there's no probability that we can assign for other transition, right? Again, we are looking at the Markov chain that every recurrent state is observing. So it's really a special class of the Markov chain. Okay. Why are we looking at this special case? Because let's first study the simple case, and then we're going to extend this class to a more general Markov chain later. Okay, because in this case, it's easier to handle. And here, the state 2 and the state 3, those are the transient states. Okay, so those are the transient states. Our question is this. So for a given observing state S, observing state here in this case also recurrent state. Okay, so given observing state S, I am interested in the probability, which we denote AIS, of reaching S. S is the observing state, starting from a state I. Here in this case, especially we are interested in the transient state I. Okay. All right. So again, starting from a state I, let's say state 2 or state 3, starting from here, that I am interested in the probability that I enter 1 or 6. There will be different probabilities depending on the shape of the Markov chain. Now, whenever I enter a recurrent state, since every recurrent state is observing state, then I will be there forever, okay? So I'm just interested in the probability that I will enter like state 1 or state 6. Maybe the answer would be something like 0.4 and 0.6 and so on. We're gonna compute that. That's the compute there, okay? So from the notation perspective, this probability should be the AIS, because in order to reach the observing state S, starting from I, right? But just for simplicity, I'm going to use just the notation AI. What is our interest? Our interest is the A2 and the A3, essentially A2S and A3S. But again, I will omit the notation S when the S is very clear to you. Okay. So let's compute that. What we need to compute is A1, A6, A2, and A3, right? A1 is what? Starting from the state I. Oh, by the way, we're going to fix S is 6, okay? So 6 is our target as an example problem. Now A1, 6. So A1 is the probability that starting from 1, I reach the recurrent state 6. What is that value? Start from here. What is the probability that I enter 6? 0, right? Why is that? Because, well, this is the observing state, so I will not go outside. I will be here in the forever, so it should be 0. Starting from 6, what is the probability that I enter a recurrent state 6? That is 1, because I'm starting here. So A1 and A6 are pretty obvious. That's why our special interest is the A2 and A3, because A2 and 2 and 3 are the transient states. I'm just interested in the probability that I enter this recurrent state or that recurrent state. Here in this case, we're going to compute the state 6. All right, so let's write down the equation. So the probability A2 is the probability, right? Now A2 can be write down the doing the conditioning that suppose that the state 2 are possible to go out like using this link and this link and this link and this link. It has 4 outgoing links. So I'm going to write down this A2 probability conditioning that I go outside using this link or this link, or this link, and this link. That is, the A2 is equal to the probability 8.2. Assuming that I take this link, then now the probability would be the A1, because I make a transition from the A2 to the state 1. Similarly, the probability 0.3 multiplied by the A2, because it's a self transition. 0.4 A3, 0.1 A6. Okay, so I just to make one step further and then write down the probabilities based on the conditioning of I'm taking this link and this link and this link. Similarly, we can write down the A3, right? And A3, it has an outgoing link of this guy and this guy. It's two guys, right? So probably 0.2, and then I make a transition to A2, so it's A2, plus probably 0.8, and then A6. So we have 4 variables and the 4 equations. So we can solve this problem. It's basically the linear equations. Okay, it's easy because here in the A1 is 0 and A6 0. So just apply this value into here. Then just 2 variables, 2 equations, and we can solve this equation. And then it turns out that we can compute the A2 and A3 like this. So what is the I again? AI is I'm starting from the transient state 2, for example. What is the probability that I will enter this recurrent state? This is A2, this is A26. Okay. Now from this probability, then we can easily make a conjecture A21, right? Because here in this Markov chain, there are only 2 recurrent states. So either I will enter this recurrent state ultimately, or I will enter the recurrent state 1. So that is equal to the 1 minus 21 over 31. That is the probability that I will enter this recurrent state. So as you can see, the A26 is larger than the A21. Why is that? Because we have more probability up to into this direction. If you roughly see that, this is 0.2, and then in this direction, it's roughly 0.8, right? So I will have a more probability, higher probability of going to or entering of 6. Okay, A3 6 has almost like 1, right? Because it's very close to A6. So it's with high probability that if we start the Markov chain from state 3, then I will enter state 6. Okay, all right. So that's the special case where every recurrent state is observing. Now, let's go back to the general Markov chain. We're going to ask the same question, but the general Markov chain. So this looks like a more general Markov chain, the previous slides, right? Here we have multiple recurrent class. So what is a recurrent class? This 1 is a recurrent class, and 4 and 5 are the recurrent class. Still here, the 2 and 3 are the transient states. Now, what is our question? The question is that the probability that the state eventually enters the recurrent class 4 and 5. Since we have 2 recurrent classes, what we are interested in is what? What is the probability that I enter this recurrent class, maybe the 1, or maybe 4 and 5? There will be a different probability. Obviously, when I enter this island, okay, so here in the starting from the, for example, like I started a Markov chain from state 2, then I'll be here and here and here and here, and then ultimately I will enter like this island. So whenever I enter this island, like 4 and 5 island, recurrent class, then the transitions within the class are not important, right? I'm not interested in what happens inside the island. Why is that? Because this is my question. And my question is, it's just the probability that the state enters the recurrent class. So after I enter the recurrent class 4 and 5, now what will happen is that after that is that, oh, there will be transitions inside because it's a recurrent class. It will not go out. But I'm not interested in after I enter the island, right? Yeah, right. So since our question is this, let us convert this general Markov chain into the Markov chain where every recurrent class is replaced by just one recurrent state that is observing. Then the answer is the same. For example, here 1 is fine because it's just observing state. But here the 4 and 5 make this 4 and 5 into the 6 and then change the transition probability appropriately. So what are the changes? For example, what is the probability from the 3 to this island? This island is the 0.5 and 0.3. So that's 0.8. Okay. What is the probability of staying at this island? Well, obviously, that should be obviously 1. That's because that's the definition of the recurrent class. We will play there forever when I enter the recurrent class because it's an island, right? Okay. Now this link is just the one link, so it should be maintained as 0.1, and other probabilities are good. Yeah, here. Okay. So we convert this general Markov chain into the Markov chain where each recurrent state is just observing states. Convert the recurrent class island into just one recurrent state that is observing. And then change the neighboring probability appropriately. Now we are done. Why is that? Because we know how to compute this using the previous slides. Okay? So using the method here, then by converting the general Markov chain that will consist of multiple recurrent classes and the transient states, then we can compute this guy. The probability that I will enter this recurrent state or that recurrent state and so on. Good. Okay, so we answered the first question that we're interested in. So what was the first question? The probability that I will enter this recurrent class or that recurrent class, starting from any like transient states. Let's move on to the second question. So what is the second question? Second question is about the expected time to any recurrent states, which is, we start from a transient state I. What is the expected number of steps until any recurrent state is entered? Again, there could be multiple recurrent classes. I'm just interested in that. Starting from the transient state, then ultimately I will enter any recurrent class, right? Like maybe this or maybe that, right? But I'm just interested in that, just the time, expected time that I reach any recurrent class. That is an interesting quantity, right? Because, well, it's kind of time to finish this transient behavior. And then ultimately I will enter the recurrent class and then I will visit that state in that island forever. Okay, so I'm just interested in the time until I go into any island, not a particular island, any recurrent island. And we call this phenomenon as observation. Whenever I enter any island, any recurrent island, then I will be observed by that island, right? Because I will not go out from that island. So okay, that's the thing that we are interested in. Again, we're gonna start from we're gonna focus first on the special case when all recurrent states are observing. You may have guessed. Then we can also make a conversion mechanism from the general Markov chain into a Markov chain that where the all recurrent states are observing. Then its answer is the same. Okay, let us denote the mu y is expected number of transitions until observation. Okay, so we can easily write down the equation. So let me use an example. So you remember the spider fly example? Do you remember that? Yeah, this was the state transition diagram. So as you see that the state 2 and state 3 are transient, and the recurrent states are the 1 and 4, and these 1 and 4 are observing states. Now let's write down the equation. So mu1 is what? Expected number of transitions starting from 1. So starting from 1, what is the time expected number of transitions of the observation? That's 0. And mu4 is also 0 because we are already in the recurrent state. So it's a trivial value. Now we're going to write down the similar values of the mu1 and the mu3 using the total expectation theorem, right? So the mu2 is that the expected number of transitions until observation starting from 2. Okay? We're going to use the similar mechanism, okay? We take a one step further, okay? So one step further and then make a transition to here and here or here. So there are 3 transitions possible. So probability 0.3, then we make a transition here, and then from that on, it's mu1. Plus, make a transition, sharp transition, and then mu2. Plus, make a transition 0.3, and then mu3. The probability, and the given I make a transition to here, what's the mu time? It's total expectation theorem, then we can write down here, right? So, yeah, this one. But here, since the mu1 is 0, then we don't need to write down the mu1 here. Okay, so I just write down here, right, like this. Okay, and similarly, you can write down the mu3, and then you get mu3. We have an outgoing here, and here, and here 3, guys. But the mu4 is 1, so forget about that. So probability 0.3, let's make a transition here. So that's mu2, 0.4, and mu3. So we have 4 variables in the 4 equations, and obviously we can compute the mu1, mu2, and the mu3. That is the what? Expected number of transitions until observation, until I go any recurrent state, right? So again, for the general Markov chain, we can convert them into the one with only the recurrent state that are observing, right? Because here, again, the transitions after I enter the recurrent class is not important, right? All right, so we're done with the second question. Third question is that I'm interested in the expected time to a particular state, recurrent state S. Again, the difference from the previous question is in the previous question, I'm just interested in the time until I just enter any recurrent class. But here, I'm interested in the expected time to a particular recurrent state. Okay? Obviously, we need to handle this question for the general Markov chain. But as you can look at the book, then we just assume a single recurrent class in this example. So we are just looking at a more restricted situation. And then sort of the develop method for that. Okay, so let's focus on the case where we have a single recurrent class. So we go back to kind of easier case. Okay. Here we are interested in the 2 different times. So first, what we are going to look at is starting from I, the single recurrent class. What is the expected number of transitions Ti to reach some particular state for the first time? Like I to the S for the first time inside the single recurrent class. For example, this is a single recurrent class, and what is the mean first passage time from 1 to 2? Because there would be a many path, like a direct path, or maybe multiple times and path, right? So there will be some expectations. So how can we compute this mean first passage time? Well, here as an example, the mean passage time from 2 to the 1. So 2 to the 1 in this case. Okay. I'm going to denote that as a TI1 because it's a mean first passage time to 1. Okay. So what I'm interested in is the T21. Okay. But again, for notation simplicity, I'm not going to use this 1 just for the simple presentation. So TI. Okay. Now we can also the same thing. The T1 is 0 because the 1 is already the passage mean passage time to the 1. So T1 is 0. And the T2 is that, again, the T2, I make a first transition of one guy and the second guy. So make a transition first one time. So we need to add 1. And then the probability P21, and the T1. And the P22 and the T2, right? Okay. T1 is 0. So this is 0. And this is a 1 plus 0.4 T2. Is equal to T2. So if we solve this is 2, that's 5 over 3. It's a kind of similar mechanism that we have used. That's the mean first passage time, okay? Now, the different time, that is that mean first recurrence time. So the mean first recurrence time, starting from S, expected number of transitions to reach S. So here in this case, I to the S. Here in this case, S to the S. The same state. That's why we call this is a recurrence time. This is a passage time. So how can we do that? So here we are using the notation TS star, starting from S, the time until to reach the S, okay? So for example, I'm interested in the 1-to-1, which is the T1 star, right? Starting from here 1, what is the expected recurrence time? Because it can return to state in 1 step or maybe 2 step or 1, 2, here 2, 3, 4, 5, 6 steps. So we want to take an expectation of all this recurrence time, the time to return to the state 1. Right? So we can write down the equation in a similar manner. So T1 star is the mean first recurrence time is that we make a 1-step transition, okay? And the 1, and then suppose that we make a transition like sub transition, then T11, and that is the time to what? Go back to the 1, right? Then that's the T1, and T1 is defined from this mean passage time. Okay, so this is essentially what? T11. Okay, now probability P12 is the probability, and make a 1 step, and then the P2, what is that? This T21. Okay, so T21 is already computed here, and the T11 is 0. So using the mean first passage time, I can compute the mean first recurrence time. And we can compute the similar thing from the 2 to 2, right? Like T2 star. Okay? So it's a good homework problem is that please compute the T2 star. Maybe the T2 star is expressed by what? 1 plus 2, right? And make a self-transition, 0.4. And then T22 plus probability 0.6. And then T12, right? So by computing this guy and this guy should be 0. And T12, how can we compute the T12? Using the same method as that we have computed the mean first passage time. Here in this case, we were computing the passage time to stage 1. But here we need to compute this first passage time to 2. So write down the different equation like we write down here. And then you can compute that and you can compute that. So what is the summary? Summary is this. So in order to compute the expected time to a particular state S, all right? And then we are interested in the two guys, mean first passage time and the mean first recurrence time. Mean first recurrence time is expressed as the mean first passage time. So we can write down the equation and then compute that, these two values. So to summarize, we have asked the 3 questions, and then we got an answer about the transient behavior of the Markov chain. First, we were interested in the probability of entering some specific recurrent class. So in order to solve the problems, we make a conversion from the general Markov chain into the Markov chain where all states, recurrent states are observing. And the answer is the same. That's the first question. The second question was that the expected time to any recurrent class, that is absorption time. And then the third question was the expected time to a particular recurrent state S. We may start from the, and we assume that the single recurrent class for simplicity. And then mean first passage time is the from the any other state I to the S, and the mean first recurrence time was the starting from the S to the S, okay, inside the single recurrent class. So those are the 3 representative questions about the transient behavior of Markov chain, and then the answers. Okay, thank you.